Physics 2211, Lab 3, Black Hole and Orbits. My name is Shineru Wachiko. Yeah. Here's our table of contents. First, we'll have the introduction and then the fundamental principles and into the data analysis / results, and then some possible errors and some further questions. Okay, for introduction, part 1, we analyze the motion of a star to determine the mass of a black hole. And for part 2, we determine the initial velocity of a spaceship to get it close enough to the moon without crashing and still be able to leave the system. This lab will demonstrate the effects of Newton's second law and its relationship with momentum. Okay, for part 1, the system would be the black hole and the star, and then for part 2, it would be the planet, moon, and spaceship. The surroundings are none. And then some a brief overview of our findings. The mass of the black hole ends up being 9.433 times 10 to the positive 33 kilograms. And then initial velocity in the x direction is negative 800, and in the y direction it's 900 meters per second. 0 in the z direction. Here's some fundamental principles. First, we have the universal law of gravitation, Newton's second law, the momentum principle, which states the rate of change in a momentum is equal to the vectorial sum of forces on a body. Note that the net force has two components. The parallel component, which is parallel to the direction of motion. Positive direction is in the same direction of the same as the direction of motion, and tells us about the change in speed of an object. The perpendicular component, which is perpendicular to the direction of motion. The positive direction is towards the center of a turning circle, and it tells us about the change in direction of an object. Note the velocity update formula, the position update formula. Vf equals Vi plus F net over m times delta t, and then Rf equals Ri plus velocity average times delta t, which is change of time. Newton's second law, which is F net equals momentum over, well, that's part of it, momentum over time. For Newton's second law, but we can derive the initial momentum is equal to, final momentum is equal to initial momentum, force of net force, delta t. And then the universal law of gravitation here, which is negative g, mass 1, mass 2, over the magnitude of the direction between masses squared time, the gravitational constant is 6.7 times 10 to the negative 11. And R is the distance between masses, just so you know. Here is our part 1 glow script. I put in my seed as my GT ID, my GT email, because the results are randomized. Here is everything that was just given. I put in the star's mass. I put in the delta t myself. Everything was given here. And then I added the final and initial momentum, the change in P, change in V. Yes. What else? And then most of these lines were already given. I just calculated the parallel and the perpendicular, basically. Here was our result. As I said, the average was 9.433. Here was the second part. Everything here was also given. We changed the initial and final, or the initial velocity in the x and y direction here. And then just the position update, velocity update, just the equations, the universal gravitation, stuff like that are all included here. Here was our result. It was obviously not a figure 8. I realized quickly that that wasn't possible for everyone, but it does work. Okay, some possible errors. Since this is a simulation, it won't always represent reality. This lab assumes there are no other forces acting on the system. Use trial and error to find the velocities. There could be more precise velocities, but that can get the spaceship closer to the moon. Sorry, that's a typo. And then what does it mean? How is the net force and its parallel / perpendicular components different from the rate of change? Mathematically, they're the same, but for the net force, you must know each individual outside factor exerting on the system, and for the rate of change, you just need to know the system's change of velocity / motion. But what if? If I wanted to predict the motion of the entire system with a black hole, a star, a moon, etc., then the computational model should have all net force acting on the object. Yeah, and all objects in a system should be exerting a gravitational force on each other. None of them would stay in the same initial spot unless one object is massively larger than others. All right, that's all. Thank you.